The concrete designed for our highways, bridges, and other structures is intended to be of the highest quality. It should consist of approved materials that are correctly proportioned and mixed, and then carefully transported to the job and placed. In practice, however, the concrete ordered for the job may not be the concrete that's actually placed. At critical points during production, transport, or handling on site, the concrete's quality may be jeopardized. Batcher mixer slips are not always a guarantee that you have the right concrete in the truck. For example, if wash water was left in the truck before it was loaded, the mix may be too wet. Or the truck driver may decide to add water if the mix begins to stiffen. So it's important and it's required that the quality of the concrete be verified before the concrete is cast. Verification is provided by conventional controlled tests performed in the field. Our first topic then is sampling. Before any of the tests can be performed, a sample of the concrete is needed, a representative sample. The concrete to be tested has to be typical of the entire truckload. The basic rule is this: don't take the sample from the beginning or end of the discharge. Take it from the first 1/3 of the discharge, but never from the first 2 cubic feet. To obtain the sample, either the entire stream should be caught in a container, or the chute should be swung over to the side. The important point is to get the entire stream. Cutting the stream in half, like this, is unacceptable. The rim of the bucket will knock some of the large aggregate out of the sample. The sample should be mixed with a shovel just until it has a uniform appearance. Then it should be covered to protect it from the sun and the wind. Samples must not be allowed to dry out. One last point. Testing must be completed within 15 minutes after obtaining the sample. Now, temperature. The temperature of fresh concrete affects the rate at which concrete gains strength, the amount of strength the concrete ultimately acquires, and the porosity of the concrete. Checking concrete temperature is simple. The thermometer is inserted into the fresh sample so that the temperature sensing portion is submerged at least 3 inches. The concrete should be gently pressed around the thermometer so that the air temperature does not affect the reading. The thermometer is left in the concrete for 2 minutes or until the temperature stabilizes. The measurement must be completed within 5 minutes after the sample is obtained. The temperature of in-place concrete is measured in the same way. Now, the air temperatures during concrete construction are also important. The high and low air temperatures must be monitored daily. Next on the list is the slump test. Variations in slump generally indicate that changes have occurred in the properties or proportions of cement, aggregates, water, or admixtures. The equipment needed for slump tests includes a standard slump cone, a standard tamping rod, a scoop, a base, and a ruler or measuring tape. The slump cone should be reasonably clean, especially inside. The surfaces should be smooth, with no dried concrete on them. Also, there should be no major dents. A standard tamping rod is smooth with a rounded tip. Makeshift rods, such as cut-off reinforcing bar, are unacceptable. The base for the cone must be strong, rigid, and stable enough to support the tester as well as the concrete and equipment. It needs to be level and firmly supported so that it won't rock or bounce. The sample should be brought close to the test location and remixed if necessary until it looks uniform. The test is begun by first dampening the inside of the slump cone to keep the concrete from sticking to it. Then the base is dampened as well, so that it won't absorb water from the concrete. But no freestanding water should be left on the base. The cone should be set down on the base as close as possible to the sample. Next, the technician steps onto the footholds at the bottom of the cone and stays there. That's why the sample and cone need to be close to each other. The cone is filled by moving the scoop around the top to distribute the concrete as evenly as possible. The filling is done in 3 layers. Each layer should take up approximately 1/3 of the cone's volume. So the first layer should come up about 2.5 inches from the base. The second layer should come up about 6 inches. That's about halfway up the cone. And the third layer should overflow the cone. As each layer is placed in the cone, it's consolidated with a tamping rod. Starting at the perimeter, with its rounded tip downward, the rod is inclined slightly to match the slope of the cone. Otherwise, the concrete closest to the cone's sides will not be properly consolidated. The rodding should go to the bottom of this first layer, but just tap the base. Each layer is rodded 25 times, with about half of the strokes made near the perimeter. A spiraling pattern should be followed as the rod moves toward the center of the cone. The strokes are distributed uniformly. As the rod is moved away from the perimeter, it's returned to the vertical. The second layer fills about half of the cone's height. It's rodded the same as the first, with one difference. The rodding should just penetrate about 1/2 inch into the first layer, not all the way down to the base. The third layer should overflow the cone. That way, the concrete stays above the cone throughout the rodding. If it drops below the top, the rodding should be stopped. More concrete should be added, and then the 25 spiraling strokes should be completed. And the rod should just penetrate the top of the second layer about 1/2 inch. With the cone full and the rodding completed, the surface of the concrete is struck off by moving the tamping rod across it in a screeding and rolling motion. The concrete surface must be level and fairly smooth. Next, any concrete that has spilled around the bottom of the cone must be removed. Otherwise, it may keep the sample from slumping properly when the cone is lifted off. However, the technician must be careful not to move the cone and disturb the concrete. Basically, both sides of the cone must be held still by pressure on either the handholds or footholds until the cone is removed. To remove the cone, both hands are placed on the handholds and downward pressure is applied to keep the cone stable before the feet are removed from the footholds. Now the cone is pulled straight up, slowly and steadily, without twisting or tilting. The removal should be completed in about 5 seconds. Slowly enough that the concrete doesn't pull on the cone. The cone is then set on the base, next to the concrete, without touching the concrete or jarring the base. Immediately, the tamping rod is laid flat across the top of the cone, extending over the concrete. A ruler or measuring tape is used to measure the distance between the bottom of the rod and the top of the concrete. The measurement should be made to a point that is directly above the center of the bottom of the concrete, not at the center of the top. The entire slump test must be accomplished within 2 minutes, as measured between the adding of the first layer and the measuring of the slump. The results of air content tests indicate the freeze-thaw durability of concrete. Air-entrained concrete with the specified air content performs much better than non-air-entrained concrete in freezing and thawing conditions. On the job, concrete can be rejected if its air content is not within the allowed range. The most popular method for measuring air content is the pressure method. 2 types of pressure meters are available and are widely used. They are referred to as Type A and Type B. With Type A air meters, the equipment needed includes a calibrated Type A meter, a tamping rod, just like the one used in the slump test, an internal vibrator, a rubber or rawhide mallet, a scoop, a strike-off bar, and a supply of fresh water. The meter consists of a measuring bowl having a capacity of at least 2/10 cubic foot and a cover assembly that includes a standpipe, a pressure gauge, and an air pump. The cover assembly also contains a number of valves and petcocks. The bowl and cover must clamp together to form a pressure-tight seal. As with the slump test, all the equipment should be clean and in good condition. It should be assembled near the concrete sample. The test is begun by filling the measuring bowl with concrete in either 2 or 3 equal layers and consolidating each one. The number of layers depends on whether the consolidating is done by rodding or vibrating. And the method of consolidation depends on the result of the slump test just performed. If the slump is less than an inch, vibrating is required. If it's more than 3 inches, use the tamping rod. And if it's between 1 and 3 inches, either method can be used. When the tamping rod is used, the bowl is filled in 3 equal layers. Each layer is rodded 25 times, and the strokes are distributed evenly over the cross-section. The bottom layer should be rodded throughout its depth, but without forcibly striking the bottom of the bowl. After each layer is rodded, the sides of the bowl should be tapped sharply with the rubber mallet 10 to 15 times around the bowl's circumference. This will close any voids left in the concrete by the tamping rod and release any large entrapped air bubbles. In rodding the second and final layers, only enough force should be used to penetrate the surface of the previous layer about 1 inch. Then, the final layer of concrete is added without excessively overfilling the bowl. When the vibrator is used, the bowl should be filled in 2 layers of approximately equal volume. After the first layer is added, the vibrator is inserted 3 times at points evenly distributed over the cross-section. The vibrator must not touch or rest on the bottom or sides of the bowl, and the concrete should not be over-vibrated. Such practices segregate the aggregate and lose some of the intentionally entrained air. The final layer is added without excessively overfilling the bowl. Then it's vibrated the same way the first layer was vibrated. Usually the surface has been vibrated enough when it's relatively smooth and looks glazed. The surface should then be struck off by sliding the strike-off bar across the top flange or rim of the measuring bowl. Then the contact surfaces are wiped clean and the cover assembly is clamped firmly to the bowl. The lower petcock is closed. The upper petcock and funnel valve are opened. And water is added until it rises to about the halfway mark in the standpipe. The meter should be gently rotated and tapped with the mallet to remove any entrapped air that may remain. Next, water should be poured through the funnel valve until it stands at a level slightly above the arrow mark on the graduated scale. The funnel valve is then closed and the level is adjusted to the arrow mark by drawing off just enough water through the lower petcock. Next, the top petcock is closed and pressure is applied with the air pump until the gauge reaches the exact air pressure required. The required pressure is known from the calibration procedure. Now, the resulting water level is read, the bottom of the meniscus on the graduated scale. This value is the gross percentage of air entrained in the concrete, or H sub 1. Then the pressure is released, and the water level on the graduated scale is read. This value is the lag, or H sub 2. The air content of the concrete is the gross percentage, H sub 1, minus the lag, H sub 2, minus an aggregate correction factor, G. Determination of the aggregate correction factor using both meters is covered in T152. The Type B test requires a calibrated Type B meter as well as the same equipment needed for the Type A test. The first step is to fill the bowl with concrete, consolidate it, and strike it off, the same as for Type A. Then the flange is wiped clean and the cover is clamped on with both petcocks open. Water is then injected through one petcock until it comes out the other petcock. With both petcocks open and the air bleeder valve closed, air is pumped into the air chamber until the gauge hand is on the initial pressure line. To stabilize the gauge hand at initial pressure, air is pumped in or bled off as necessary, and the gauge is tapped lightly. Next, both petcocks are closed and the thumb lever is pressed down. This releases the air into the bowl. The sides of the bowl are tapped sharply with the mallet, and the gauge is tapped gently with the fingers until the dial hand stabilizes. This is the gross air content percent. From it, the aggregate correction factor is subtracted. The result is the net air content percentage of the concrete. The unit weight, or density, is determined simply by weighing a known volume of the concrete. The same equipment used for air content testing is needed, as well as a measuring container, or measure, a balance or scale, and a strike-off plate. The balance or scale must be accurate to within 0.3% of the test load. The measure must be a watertight cylindrical container whose capacity depends on the size of aggregate used in the concrete. For 1-inch maximum size aggregate, a measure with a minimum capacity of 0.2 cubic foot should be used. If the aggregate has a maximum size of 1.5 inches, the measure's minimum capacity should be 0.4 cubic foot. And for 2-inch maximum size aggregate, the minimum capacity should be 0.5 cubic foot. Since the air content meter's bowl has a capacity of 0.2 cubic foot, it can be used as the measure when the concrete contains 1-inch maximum size aggregate, as is becoming more common in pavements and bridges. The first thing to do is place the empty bowl and strike-off plate on the scale or balance and record the weight. The bowl is then filled in 3 equal layers of concrete, with each layer properly consolidated. Consolidation requirements are the same as for the air content test. If the slump is less than 1 inch, you vibrate. If it's more than 3 inches, you rod. And if it's in between, you have the option. The concrete surface is struck off and finished using the strike-off plate. The bowl must be exactly level full. Then all excess concrete is cleaned off the outside of the bowl, and the filled bowl and strike-off plate are placed on the scale or balance. The net weight of the concrete is determined by subtracting the empty weight of the bowl from its filled weight. To calculate the unit weight, the net weight of the concrete is divided by the calibrated volume of the bowl.